In the third case, we now have the two B ligands trans to one another, but the two A's cis to one another and the two C's cis as well. This is different than the first two isomers that I have shown. The final isomer on this slide has the two C's cis, or two C ligands trans to one another, the two A's cis and the two B's cis. So now let's look at the nomenclature for all the geometric isomers of CONH3 2H2O2CN2+. This is just like the example that we went through with A, B, C, and M. Here's the first case where the two amine ligands are 180 degrees from one another. The two H2O ligands are 180 degrees from one another, and the two CN ligands are 180 degrees from one another. The name of this compound is transdiamine, transdiaqua. You can leave out the trans before the dicyano because by geometry, the cyano ligands are forced to be 180 degrees. So this is dicyano-cobalt-3. In the second case, we still have the two NH3s 180 degrees from one another. This time, the two aqua ligands are cis to one another, and the two CN ligands are also cis. So we name this one transdiamine, cis-diaqua. In this case, since the diamine is trans, since the amine ligands are trans and the aqua ligands are cis, the cyano ligands are required to be cis as well. So this is transdiamine, cis-diaqua, dicyano-cobalt-3. In this case, we have the two waters that are 180 degrees from one another. So that's transdiaqua. The two amine ligands are cis to one another, cis-diamine. This forces the two cyano ligands to also be cis. So the correct name for this compound is cis-diamine, transdiaqua, dicyano-cobalt-3. In the fourth case, we now have the two cyano ligands trans to one another. So this would be trans-dicyano. The two amine ligands are cis to one another. So this would be cis-diamine. The two aqua ligands are also cis to one another. You can omit or include the cis if you want to. The correct name for this compound is cis-diamine, cis-diaqua, trans-dicyano-cobalt-3. Now what happens when all of the ligands are cis to one another? We need to look at an optical isomer next. In this case, A is 90 degrees from another A, so it's cis. B is 90 degrees from another B, so it is also cis. And the two C's are 90 degrees from one another, making it cis as well. When you have three different ligands that are all cis to one another in a compound with this formula, it must become an optically active isomer. To note that it's optically active, we use the RS nomenclature. So the correct name for the two compounds formed from this are RS cis-diamine, cis-diaqua, cis-dicyano-cobalt-3. Now, we are able to draw all of the geometric isomers for a given formula if we do it systematically, and I'm going to provide a handout that will help you do that. If you have So this table will help you think a little bit about that. If you have three different types of ligands within your compound, such as Ma2B2C2, the total number of isomers that you should draw are 6, and you should have 2 of those isomers that are enantiomers. If you have 4 different ligands, such as Ma2B2CD, you should have 8 geometric isomers, and 4 of those should be enantiomers. If you have 5 unique ligands, that gives you a generic formula of Ma2BCDE. That means 15 different isomers can be drawn, with 12 of them being enantiomers. And finally, if you have 6 different types of ligands, the formula would be MABCDEF, and the total number of geometric isomers that you will draw are 30, and all 30 of them are optically active. Using the handout, I will show you how this octahedral numbering scheme helps you to draw geometric isomers for octahedral geometries. So now, you have 3 questions to consider for your homework for this week. Next time, we will spend our time working on optical isomerism and introduce the idea of coordination number and oxidation state.